And Dr. Gautam Paul is the Associate Professor and Head of the Cryptology and Security Research Unit at the Indian Statistical Institute, Kolkata. He is also a visiting professor at the Center for Quantum Engineering, Research and Education, TCG Crest, Kolkata. He obtained his Bachelor of Engineering in Computer Science from IIEST Shibpur, formerly Bengal Engineering and Science University, his Masters of Science in Computer Science from the State University of New York at Albany, USA, and his PhD in cryptography from the Indian Statistical Institute, Kolkata. Before joining ISI, he served as an assistant professor in the Department of Computer Science and Engineering at Jadavpur University from 2006 to 2013. And currently, he leads the ISI's Cryptology and Security Research Unit, focusing on classical and quantum cryptography. Dr. Paul received several distinguished honors, including the Alexander von Humboldt Fellowship from Germany in 2012 and the Young Scientist Award from the National Academy of Sciences, India, in 2013. His research spans classical cryptography, quantum computation, and quantum communication. Since 2024, he has been serving as the regional coordinator of the Mathematical Olympiad for the West Bengal region under the National Board of Higher Mathematics, India. To date, Dr. Gautam Paul has supervised 6 postdoctoral fellows, 16 PhD theses, 24 master's theses, and around 100 undergraduate products. He has authored over 130 peer-reviewed papers and 2 technical textbooks and also delivered more than 150 invited technical lectures along with over 100 motivational talks including 2 TEDx talks. And now it's really an honor for all of us to have Dr. Gautam Paul over here for the guest lecture. Over to you, sir.
I hope you can hear me. Mm, yeah, so let me share the slides. One second. Can you please see the screen? Yeah. Okay, okay. Fine, fine. Right. So, yeah. Okay, let me share differently because I think this is better. Okay. Can you see the diagram? I have shared one diagram on the screen. No? It should be there. Yeah. So, can you see what the diagram? There is some mirroring happening. I don't know why. Yeah. And what about the diagram, like written crypto system and all? Okay, okay. Nice, nice. Okay, so so this is about cryptography and what what does it mean in the classical and the quantum world. So that's what I'm going to speak. So this diagram is very important to understand why we needed a transition from the classical to the quantum domain in terms of cryptography. Okay. So broadly, we can classify a crypto system into two categories. One is symmetric or private, the other is asymmetric and public. Under symmetric, so the name tells you the meaning. Symmetric or private means that there will be one secret key shared between the sender and the receiver, and it will be the same. So the same key will be used for encryption and the same key will be used for decryption. On the other hand, the asymmetric or the public key paradigm, there is an encryption key which is made public so that everyone can encrypt, and there is a decryption key which is kept private so that only the recipient can decrypt. So that justifies the names that are there. And under symmetric, we have two other subcategories. One is called block cipher, the other one is called string cipher. Okay. The block cipher, as the name suggests, divide the message into fixed length blocks. So the block length could be 64-bit, 128-bit, 256-bit, etc. And then it applies the encryption algorithm on each block independently. So it's kind of a iterative process. If you have to encrypt 1 gigabit of file, then it will encrypt the first the block size, maybe 128-bit, the next 128-bit, and so on to repeat the process. On the other hand, stream cipher, if we think, it is nothing but a bit by bit XOR operation of the original plain text and the key stream, the secret key stream. So that means you encrypt bit by bit. In other words, the message is viewed as a stream, a continuous stream of bits, and you encrypt one bit at a time. So that is stream cipher. Now, some typical examples which I'm sure many of you have heard of, and you can Google search and find out more about them, is that in the famous block cipher. What is the famous block cipher? One is AES, the Advanced Encryption Standard. So that is the de facto standard of a block cipher that is used commercially across the world in many applications. And it was standardized by NIST, National Institutes of Standards and Technology, in the year 2001. Before that, the standard block cipher was DES, or Data Encryption Standard, which was replaced by Advanced Encryption Standard, or AES, in 2001. Stream cipher. What are some of the famous stream cipher? Well, you have the Snow stream cipher, which was used in 3G networking, 3G wireless crypto. Then you have the E0 stream cipher, which is used in the Bluetooth encryption. Then you have the RC4 stream cipher, which was used earlier in almost all the internet browsers, and now that has been replaced by Chacha or Salsa. So you can guess probably that box ciphers are heavier and the stream ciphers are lighter because the operation is less. Operations have less complex. So the question may come that if we are happy with string cipher, see, I'm going to spend a lot of time on this slide because this slide has a lot of story, and all this story actually connects our journey, the journey of the crypto world from the classical to the quantum. So if we have to understand the fundamentals of security in the classical domain and in the quantum domain, and why this shift happened, how this shift happened, and what are the implications, then this hierarchical structure is very important, and it's important to know where does exactly the quantum cryptography fits. So that's why I'm spending so much time before I switch to the quantum cryptography direct. So as I was saying that if symmetric key cryptography has a lot of applications that I have already mentioned, starting from online transaction to e-commerce to network security to internet browser, then why was the need of asymmetric and public key cryptography? Famous public key cryptography example is RSA. Even if you don't know the algorithm, I'm sure all of you have heard of it, the reverse Shamir Adelman, famous RSA algorithm, and the elliptic curve based cryptography. Right? So those are famous asymmetric and public key algorithms. So the reason symmetric and private key cryptography, along with it we have asymmetric, is symmetric cryptography has a requirement that we have to share the secret. Now imagine the sender and the receiver, they are sitting in a room and they are tossing a coin, choosing some random string and writing it down, and then going apart in two different parts of the world. So now because they have shared the secret key, they can use the same secret key to encrypt and decrypt. I mean, to convert the message into a random looking ciphertext and to get back the message at the receiver end. And that's the inverse operation. They will use the same secret. Now, what is the problem? This is not practical. Means we cannot always expect that the sender and the receiver will physically meet. They may not physically meet ever, especially in today's world. The sender may be on one side of the Atlantic and the receiver may be on the other side of the Atlantic, and over telephone they decide that okay, from tomorrow we are going to use cryptographic communication. So now the question is, how will they share the key? Because it becomes a circular problem, and egg versus chicken problem, that which one came earlier. Because if they can share the secret key, then they can share the message as well from one end to the other, because the key has to be shared from one end to the other. The message also has to be shared from one end to the other. So why do it in two steps? You share the message directly. So that means this is a big problem, that sender and receiver far apart. They want to use cryptography, but they can't share it. So there this asymmetric key and public key comes handy, which works as follows. Using number theory, or different mathematical operations, you can actually create two keys which we call a pair of keys. So one is the encryption key, one is the decryption key, which are different bit strings, but they work as the inverse of one another. Means that the receiver, let's say, whoever wants to be the receiver, can create this pair locally, the encryption key and the decryption key locally, and can float the encryption key in his or her public domain, so that everyone around the world can get hold of the encryption key and encrypt whatever message they want to send to the receiver. However, the receiver will not make the decryption key public. The receiver will keep the decryption key at his or her own disposal And whenever any encrypted message will be received at his or her end, he or she will decrypt that using the private, secretly kept decryption key. And if we want two-way communication, no problem, because now another person will act as receiver and initiate the communication. So that's the beauty of asymmetric. So what we can do, we can combine an symmetric and asymmetric key together. Right? So typically the asymmetric key and public key cryptography, because it relies on heavy number theoretic operation, it's typically slow. And symmetric and private key crypto operations are much faster, and therefore they are more practically applicable, more commercially applicable. They have more real-time applications. So we make the best use of both. So use the asymmetric or the public key cryptography to share the secret key that will be used for future symmetric or private communication. Okay, this is very important to understand. So for symmetric and private key communication, we need a same key to be present at the sender and the receiver. It means that has to be shared when they are remotely situated. And this key sharing can be performed using one session of asymmetric or public key communication where there is no need of key sharing. Encryption and decryption will be done locally. Encryption locally at the sender end, decryption locally at the receiver end. And the very first message that the sender will send to the receiver is the intended secret key bit string for future symmetric or private communication. Okay, so once we understand this, then we can appreciate that in real world, whether you carry a laptop or your Wi-Fi device into a new Wi-Fi zone, or you logging to an e-commerce server for online purchase, Amazon or Flipkart, whatever, or you log into internet banking and perform a transaction on your account, all of these happen with the help of a combination of these symmetric and asymmetric paradigms. So first, asymmetric paradigm to share the secret key, and then the symmetric key paradigm to actually use the real cryptographic communication. So this, in short, what I just described is the whole gamut of physical crypto system summarized in one slide. So asymmetric slower, symmetric faster. Therefore, we need symmetric in practical communication. However, symmetric requires prior key sharing, for which the asymmetric guy comes to help. Right? We could actually perform the entire communication using asymmetric key only. We could discard the symmetric key completely. However, because asymmetric key is super slow, we have to make best use of it. We use it only once to share the key, and then switch to symmetric key with shared key so that we can communicate faster. So at this point, any question in the audience, or any point that is not clear, please ask question. Anybody in the audience? Hello? Yeah, I need to hear yes, no, something. No. So I assume there is no question. Next, in 1994, when Peter Shor discovered his famous Shor's factoring algorithm, then that was a blow to the asymmetric or the public key world. Because the most famous, the most widely used asymmetric or public key crypto system was RSA, which the security of RSA was dependent on that if you have two numbers, you can multiply them very easily. But if you have a large number, factorization of that large number is hard. So the security of RSA was dependent on the hardness of factoring. And though classically factorization is very hard, in 1994, Peter Shor published the quantum algorithm which could factorize any number in polynomial time, polynomial in the size of the number. So what does it mean really? It means that now an attacker sitting in the channel, if it has access to the factoring algorithm as a black box as a tool, then the attacker can break the system, find the secret key, and compromise the system. Okay. So that's the implication. Now, the sender and the receiver may not have a quantum computer, but they have to assume that the attacker has quantum resources because the attacker can be powerful, the attacker has a lot of money, the attacker can buy all the resources of the world. So we can model any attacker like this. So the problem is now, if the asymmetric and the public key crypto system is gone, then this symmetric or private key crypto system, what happens to it? Well, it still remains secure in the quantum world. That means we can safely use the block cipher like AES and the stream ciphers like Cha-Cha Salsa that are used nowadays in TLS 1.3, networking protocol, SSH, Telnet, etc. with possibly some adjustment of the key size. So that's fine. But how to share the key? Fine, we'll do symmetric and private key communication safely and securely in presence of a quantum-enabled adversary. But how, in the first place, we will share the secret key? Because that is a mandatory requirement. So here comes quantum cryptography. In short, quantum cryptography was started to replace the asymmetric or the public key cryptography as a substitute of the classical algorithm of key sharing. And then it is understood that the sender and the receiver will switch to the symmetric or the private communication. So quantum cryptography in its preliminary stage is nothing but a replacement of the classical asymmetric or the public key algorithm in terms of the secret key sharing. So to cut the long story short, what is the goal of such quantum cryptographic scheme? The goal is To use quantum mechanical system, to use quantum physical system, to share a classical bit string. So at the end of the quantum crypto protocol, the sender and the receiver will have shared a common classical key or common classical bit string that will be used as the secret key for symmetric or private communication. Okay. So I think this part is now understood.
Yes, sir.
Yes. So any question on this part? I will then switch to the quantum. Okay. So let me share the another thing. So now what I will do, I will switch to the quantum cryptographic algorithm, maybe 84. Okay. Hmm. So can you see the page 29 of my slide here?
It's not visible.
Okay. I think now it will be visible.
It's visible now.
Yes. Yes, yes. Thank you. So what is BB84? So the acronym BB stands for Bened and Rasa. BB84 is a quantum key distribution algorithm that was discovered in 1984 by Bennett and Prasad. So it goes by their name. And it was the first algorithm that came in order to replace the asymmetric key algorithm or the classical asymmetric key algorithm which we use to share secret key. So BB84 became the de facto standard after Shor's algorithm was discovered and after a fear of, getting our classical key sharing algorithm compromised, that these things came, then BB84 became the de facto standard for quantum key distribution, means sharing a classical bit string using quantum mechanics and then use that bit string as the secret. So the history of BB84 goes as early as 1970, where Stephen Weisner published something called conjugate coding. Okay? That did not have any foolproof discussion on the security. So finally, Bennett and Prasad in the 1984 paper, they came about a scheme which gave security against quantum adverse. Okay. So what is the basic idea? Let's understand. So to transmit 0 and 1 securely, we choose some basis plus cross basis. So So I guess the audience is introduced to this basis concept, right, in the quantum. Okay, good. So as you can see, that class is the horizontal and the vertical basis polarization. If you think photon polarization as the physical representation of the quantum information, then the horizontal and the vertical polarization vector can be represented as 0 and 1, so that can become one basis. And diagonal polarization, the northeast and the northwest, which are nothing but superposition of this horizontal and vertical polarization, namely 0 plus 1 by root 2 and 0 minus 1 by root 2, so that can be considered another basis. Now, we know that when we want to measure a quantum state, then basically we have to take the inner product of that quantum state. If we are doing projective measurement, then inner product of the quantum state and the particular basis in which we are measuring. And that will give us the probability of the state collapsing into the particular basis state. So it is our measurement result. So using that simple property, BB84 is designed as follows. So 0 can be encoded into either plus basis or cross basis. 1 also can be encoded in either plus basis or cross basis. So once you select a plus basis, we can, with loss of generality, represent 0 by the k 0 vector, horizontal polarization. You can represent 1 vertical vector or 1 vector. Okay. Similarly, in the cross basis, we can represent 0 as the northeast vector, 0 plus 1 by root 2, and we can represent 1, I mean the classical 1, as the northwest vector, 0 minus 1 by root 2. So we take any basis, we encode 0 to 1 qubit, encode 1 to another qubit, and if you use only a single basis, then what is the problem? Then anybody can measure in that basis, get the information and reproduce. Because if the sender and the receiver use the single basis, then the attacker, so that basis will be known to everyone. So the attacker will also measure in that basis to get the information perfectly. Okay. So because of that randomization requirement, we need to choose the two bases random. Okay. And similarly, Bob also needs to measure in random basis. Now, because Alice is encoding in random basis and Bob is measuring in random basis, so sometimes their bases will match and sometimes their bases will mismatch. So positions of the basis match will give the keyless. Fine. So in short, this diagram explains what explains the sketch of BB84 protocol. So we're going to spend some time on this diagram. So in this diagram, from left to right denotes the position of the bits. That means, 0. If you look at the first row, 0 is the first position, 1 is the second position, then 1 the third position, then the fourth position bit is 0, and so on. So left to right are the positions. Okay, and we'll say quantum particles like photon in different polarization in that manner. So there will be photons sent from the first 0, 2 photons sent from the next 2 1s, then 1 photon from the next 0, another photon from 1, and so on. So 1, 2, 3, 4, 5, 6, 7, 8. So the 8 bits from here, photons will be sent at least in 8 components. So that's an understanding. Okay. Now, if we go down from top to bottom, as the different rows, then it represents time. okay, or the different steps. That means the first row corresponds to the first step of the algorithm at time t1, second row, step 2 of the algorithm at time t2, third row is the next, and so on. So I will explain time-wise, the chronologically, what is happening. So let us focus on the first row, ignore the rest of the rows. So the first row, we write Alice's bit. So we assume Alice is the sender and Bob is the receiver. So therefore, the sender, meaning Alice, has some randomly chosen bits at her own disposal locally, which she wants to share with Bob. So that means Alice has this bit string 01101001 that may have been generated by coin toss or by some natural process. And now Alice wants to share this with Bob. That is the so that is step 1. So in step 2, what will Alice do? Now Alice will randomly choose a sequence of bases. Okay. So what are the possible bases? We already discussed that we'll use 2 bases instead of 1. That is plus basis and cross basis. And Alice chooses randomly means she will choose a sequence of class and cross random. So she randomly decides, okay, the first 2 bits to encode in plus basis, the next one in cross, the next one in class, and cross plus, etc. Okay, so this is a random sequence of class and cross without looking into the bit string. Now the third step means that, so when you look at the third row, you have to simultaneously focus on the first and the second row in the same column. So we'll read column wise. So we'll read column wise the third row in context with the the first row. So Alice polarization. So 0 when we encode in class basis, we have already discussed 0 in class basis is encoded as the vertical polarization, and 1 is class basis the horizontal. So 0 in class, we get Alice's polarization as the vertical vector. So now this is the physical encoding of the logical information 0 in the chosen class basis. So you see the upward arrow is nothing but a physically vertical superposition of a photon. Okay. So that's the physical representation. Similarly, 1 in plus basis is represented as a horizontal vector denoted by the horizontal arrow in the third row. Then 1 in cross basis is a northwest vector, 0 in plus again vertical, 0 in 1 in cross again west, and 0 in cross northeast, 0 in northeast, and 1 in plus rightward arrow. So the third row represents the polarization of photons. Then we choose to represent the logical bits in the first row in the Alice's randomly chosen basis of the second. Okay. So in that sequence. Now, what will Bob do? Bob will choose another sequence of bases randomly. So you see plus, cross, 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 plus, cross, plus, plus. You can write whatever you want. And now, after receiving the physical qubits in the third row, Bob will measure them in Bob's basis and get the measurement result. So now let us focus on the third, fourth, fifth row together in this table. So third, fourth, and fifth row together. So third row arrows denote the input vector, and Bob's basis represents the measurement operator as the receiver end, or at the Bob's end, the measurement basis. And the third row represents the measurement result. So let's look at column wise now. Let's focus on third, fourth, fifth row together, but column wise. So the first column, you see a vertical arrow, right? You measure it in class basis, you get a vertical arrow because the dot product, the inner, the vertical vector is 1 with the vertical vector of the plus basis, and inner product is 0 with horizontal vector of the plus basis. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 plus 1 is 0. So that means 1 plus 0 is 1, 0 with probability 1 will get the collapsed state aligned with vertical polarization. So that means we can decode the information effect. Okay. Now, what happens in the second column, if you see that Alice's polarization is horizontal, right? Encoded in class basis. The Bob's basis is cross basis, which does not match with the class basis. So if we take inner product of Alice's polarization, which is horizontal, with the diagonal vector, we have 50% probability of getting the northeast vector as our collapsed state after measurement, and 50% probability of getting the northwest vector as the final state after our collapse. So that means now randomly, sometimes the Bob can recover the bit that was originally sent, and sometimes Bob cannot, because of this randomness. Uniformly, it is prone to error, right? Because the bases are not matching. And this is purposely done. So I will explain why. After Bob's measurement, you see that they have public discussion. What do they discuss? So Alice and Bob publicly discuss that where their bases had matched and where their bases had not matched. The positions corresponding to where their bases had matched, because they are now announcing their bases publicly, they will discard those positions, and where their bases will match, they will keep those positions because they are guaranteed to match the encoding bits with the decoded bits. So that is guaranteed. So removing the columns, now you can focus on the columns that are remaining. After removing the columns where the basis does not match, means either in the second and in the fourth row, depending on that, we eliminate the particular columns, and the remaining columns contribute to the secret key. So you know the shared secret key at final row we show at 0, 1 and 0, 1. So now there are several questions that you can ask right at this diagram. Looking at this diagram, that what gives rise to the security. So the first question, why can't Alice and Bob discuss publicly anytime? Because they have chosen their bases locally. So why the public discussion has to wait until Bob's measurement happens? That is very critical to the security. Because when does Bob's measurement happens? When the photons transmit completely from the quantum channel and go to the receiver. So if the public discussion happens before Bob's measurement, still right quantum channel. So then we'll know when the basis has matched. And data card will measure basis in the corresponding positions to get full information 100%. So this public discussion of which basis they had chosen has to happen after Bob has received all the qubits, and in the quantum channel there are no qubits flying anymore. So that is the logic. Second argument that one can make is that suppose in the quantum channel the qubits are flying, what if Eve creates a copy of the qubits with herself, okay, which measure flying qubit pass to the, so one will not be aware of the fact that the data has made a copy of the state. So here comes another very important principle in the quantum information that's called no cloning theory. It was discovered by Iiit and Zurich in 1980. The famous no cloning theory states that you cannot create a copy of any arbitrary unknown state. Of course, if you know the quantum state, you can create a copy as many times as you want. If you know a state is 0, you can create a copy. If you know a state is 1 or 0 plus 1 by root 2, no problem. You create copies as much as you want. But if your state is unknown, then you cannot create copy with 100% success. So that result is no cloning theorem, and that helps us. And that tells us why any attacker cannot actually have additional photons at the attacker's disposal and create copies of the flying photons to the attacker's photon so that the measurement can be done later. Cannot do it. It has to let the flying qubits go without copying. It can maximum it can do is to try to do some measurement and resend. So that is called the famous measure and resend data. The problem of that is because attacker will be measuring without knowing the basis, because the box measurement has not yet happened, public discussion has not yet happened. So if the attacker has to attack the qubits, that has to happen after the third row in this table. So between the third row and the fourth, when the photons fly in the quantum channel. And that tells us that attacker will not have any advantage. So this is in crux what happens in the quantum domain, in the quantum security. So the next, an obvious question is that is quantum cryptography the only applications of is quantum key distribution the only application of quantum cryptography? The answer is not. There are variants of QKD as well as there are variants of non-quantum key distribution quantum crypto as well. So there are quantum secret sharing, which is analogous to classical secret sharing. So what I discussed is basically the main pillar of quantum cryptography, which is quantum key distribution, which is used to replace the classical asymmetric key-based communication so that you can perform the symmetric communication safely and securely even in presence of quantum attacker. But there are other applications such as quantum secret sharing, quantum multi-party computation, which is similar to classical multi-party computation, quantum private query, which is related to client-server-based communication, where the client does not know additional information from the server than whatever was the query, and server, does not know on which data the client has queried. Then position-based quantum cryptography, that means certain quantum states can be revealed only when the person who is performing the measurement is located at particular physical locations. Okay. So, post-quantum cryptography, is the current buzzword. Everyone is thinking about it. What it means is that just because RSA and elliptic curve cryptography is shattered, the question is the quantum key distribution the only way to replace it? There are other classical schemes which are attacked by Shor's algorithm or the variants of Shor's algorithm that survive quantum attacks so far, which we can use. So there comes the post-quantum crypto protocols. They are purely classical algorithms implemented in purely classical machines, and yet they have the property that they can resist any sort of quantum adversary or quantum attacker so far as our current understanding goes. And not even Shor's factoring, but any quantum algorithm you can think of, Simon's algorithm, Shor's algorithm, any algorithm, they are not fully. So these are classical algorithms that the sender and the receiver can use safely to communicate even in presence of a quantum attacker using ordinary classical machines, ordinary classical channel. So that's the goal of post-quantum cryptography, and we know that National Institutes of Standards and Technology had launched a competition to select PQC standard algorithms from 2016 to 2022. It's a pretty long competition. And finally, they have selected 4 candidates so far as the finalist of most wanted candidate. So, you know, lots of independent interest. So with that, I will stop and take any questions that you may have. So any question? If speaking is a problem, then you can take questions.
Sir, could you please explain about quantum mechanical system to use quantum physical system?
Nandu, what is your question?
When you are
Oh,
saying
okay. Understand. I understand what you mean. So you see that whenever we have to represent information, right, you need some physical representation. So in the classical domain, when we have to represent 0 and 1, we either choose high voltage versus low voltage to represent 1 and 0, or high current versus low current, or a capacitor, highly charged versus discharged. Right.
Yeah.
So in the quantum domain, we need quantum particle and their quantum state to represent our classical information 0 and 1. So we can either use photon and their horizontal and vertical polarization to represent 0 and 1, or we can use electron, their spin to represent 0 and 1. So for example, plus half and minus half, two spins can represent two property. We can use angular momentum, kind of degree of freedom, to represent quantum state. We can represent, atoms and molecules, and atoms in ground state to be 0, and atoms in excited state to be 1. So physically, we can represent, multiple quantum subjects as potential candidates for the representation of the information zeros and ones. The advantage is that in quantum, because we have superposition of state, because we can have any combination of horizontal and vertical polarization. Therefore, we can represent superposition of zeros and ones. I mean, combinations of multiple states together. So that's an advantage. But physically, there are many ways in which you can encode quantum. Any other question?
Guys, anyone have any questions?
Guys, if any one of you are having any questions, you can come forward and ask that.
Sir, could you please explain about PQC with examples?
Okay. So let us. Okay. Let me share something to internet.
What I am asking means you said lattice based, multivariate, hash based. We don't know what are they. What are those? Could you please explain about them?
Yeah. So you can see here, I'm sharing the screen. Can you see that?
Yes, sir.
Yes. As I was telling that this NIST competition has ended in 2022, and they have announced few candidates as the current PQC standards. So they have recommended, okay, this candidate for encryption, this candidate for key exchange, this candidate for signature, etc. So if going into the details, if we want to understand what they are dependent on. So for example, if you look at this table, for lattice-based post-quantum cryptography, we have Crystal, Kyber, NTRU, and Saber as the candidate, right? So, you know, what does it mean by lattice-based crypto system? So lattices are nothing but vectors with integer linear combinations, and in that vector space, what we ask is that what are the hard problems that gives rise to security? So one problem, for example, is the closest vector problem, meaning in that vector space of lattice, if you are given one coordinate point, finding the closest lattice point to that is a problem, because lattices are integer coordinates, right? So they are, not integer coordinates, but integer uh, combinations of the basis vectors. So basically, they are integral multiples of the basis vectors. So that means they are like grid points. You can have either horizontal grids or slanted grids, but the lattice points are sitting on the corners of any grid type structure. So you have a grid point. What is the closest grid point? Mathematically, that point, finding that is very, and the security of lattice-based crypto system is based on that property. That means if an attacker has to decrypt the crypto system without the secret key, then the attacker has to solve this particular hard. So the crypto systems, depending on this hardness, is called lattice-based crypto systems. And there are some examples here given on the screen, which individually you can go and study exactly what are the functions they are using, mathematical functions they are using. Similarly, code-based crypto systems, right? So we know that the purpose of coding theory is to provide error resilience or noise resilience. That means whenever you send any signal, this is irrespective of classical or quantum. Whenever you send a classical signal or a quantum signal in a communication channel, it's bound to be subject to noise, and therefore some information will be distorted. So at the receiver end, you try to decode it and get rid of the noise or get rid of the errors. How do you do it? By using the theory of error correcting codes. That's a traditional topic in classical information theory. We can use Shannon code, Hamming code, CRC code. There are many different codes. Even in quantum domain, we can use CSS code, Shor code, many coding schemes to add redundant bits, redundant qubits, so that we can detect the noise and correct the noise at the receiver end. Now, there is no cryptography in this coding and decoding error removal process, right? The theory of error correcting codes is completely different from the subject of cryptography. But the code-based cryptography is based on the paradigm that decoding is a very hard problem. Unless the attacker has access to suitable decoding parameters, only the receiver can do the decoding, not the attacker. Here, decoding means decoding the theory of error correcting codes. Decoding, like decoding of Hamming code, or decoding of, let's say, MacLeese code that is given. Because decoding is a hard problem. So we can do system based on the hardness of coding theory. Encryption will be nothing but adding the noise, and decryption will be nothing but removing the noise. So your encoding becomes encryption and your decoding becomes decryption. Okay? So that is the idea behind code-based crypto. So these are some of the examples that I can think of.
Thank you, sir. But before RSA encryption is solvable by using Shor's algorithm. It can factorize large numbers like that.
Right.
Lattice can be solved by if quantum computer can solve those lattice points, then it also breaks, sir.
No, so right now, so far, just like we do not see any attack on the cipher and stream cipher in the classical domain. Similarly, we do not have any attack on these lattice code-based multivariate crypto systems in the quantum domain, and therefore they are post-quantum crypto. Means they quantum secure. In future, there may be an attack. That's a different thing. So far, in none of the quantum attack models, these systems are vulnerable.
If any algorithm breaks those, then they can also break, sir.
Yeah, they can also break, but then it's have a huge implication. For example, if you can break code-based crypto system in polynomial time by solving the decoding problem, and because coding-based crypto, decoding is NP-complete problem. So basically, then in the quantum domain, you will collapse the P versus NP hierarchy. So which the theorists believe that is unlikely to happen. Right? It's not yet known whether P is equal to NP in quantum domain. We believe that it is not. So it's a very hard complexity theoretic, issues, and they will come up.
Thank you, sir.
Yes. Thank you.
Thank you, sir. This is such an edifying lecture, fully packed with knowledge and learning. It's a feast having to attend your lecture, actually. And on behalf of all the participants and the team, I sincerely thank you, sir, for such an enlightening and highly engaging session on the topic you have covered. Today's lecture also guided us through the fundamentals of classical cryptography, including symmetric and asymmetric systems and their real world applications in online security, e commerce, and even data protection. Your intuitive explanation, analogies, and structured approach made even complex concepts highly accessible, sir. That's really so generous of you. And we also explored the realm of quantum cryptography, where you introduced us to BB8 core and the quantum key distribution, showing us how quantum principles replace classical systems and communication. The session beautifully bridged the theory and practical applications, highlighting the evolution from classical to quantum crypto systems. This lecture not only deepened our understanding of cryptography, but also inspired us to think about how quantum technologies will transform the data security and the future of secure communication. Thank you, sir, for your time, guidance, and for making such a complex topic both understandable and captivating for all the participants. We really loved this session, sir. And we can wind up this
Thank
session
you.
with a very big round of applause for all his efforts, time, and insights. Thank you, sir.
Thanks a lot.
And to all the participants online and offline, whoever are attending the session, please fill out the Google form which is available in the Google Classroom. The link will be available in your Google Classroom created. Please fill out the form to confirm your attendance as well as to give the feedback of both of these sessions. I hope you have